the exponential map. I've tried to explain how important it is, but I haven't really completely finished what I would like to say. So let us recall what we know about this very important map. So the properties we know so far. Let me just say, you know that expression, what this is some sort of microcosm. Because if you can really get a feeling for what's going on with this exponential map, I think you can get a feeling for many important things. And it's in itself important. One of the properties that we know, it's locally biholomorphic. Surjective homomorphism of groups. Many math words here that you need to know. And in order to study such a thing better, I recommend that you draw a picture a general picture so you have a group G, which I always draw as a box, and it has an identity in it which I always call 1. But in the case of plus here, the identity will be called 0, because you add 0 and you don't change, but we call it plus. But I always write identity, and this if you have, say, a G and a homomorphism G hat, I'm repeating what I said yesterday, but it's important, into some other group G, the image of phi is certainly contained in G hat. Who knows how it's contained there? Here we already know the image of the whole thing, so it's because it's surjective, but in general you don't know this. And you have this map, phi, and phi takes G to G hat, and it has a certain image. And we showed yesterday that the image itself is itself a group, because the image of a homomorphism is a subgroup of G hat. It's a general statement of G hat. Just because it's a homomorphism, it's a good kind of mapping, and is naturally identifiable with G modulo the equivalence relation that defines the fibration. Yeah. And so I talk a little bit in the physics seminar. This is the first basic example of principal bundle. So, because there is a group action which gives this, and we know if you have some G hat, you want to know what the fiber is over G hat, and if you take any G in that fiber phi inverse of G hat is just, you take any G here and you push it around with the kernel of this mapping, and this is a general phenomenon. So we write this thing as n, and n is in this case the kernel of the mapping. And phi, which is the set of elements G, such that phi of G is equal to the identity. Here's the identity downstairs, and identity hat downstairs. So what you do is what you get here, what you get in this fiber is everything that you get by pushing it around. Okay, so that's the picture. And that's what I indicated yesterday, and that's the picture you should get into your brains, because it's very, very important. And somehow it is not trivial, so you need to practice with this picture. Of course, the key that I wrote here is the key that makes this really work is that this thing N is a normal subgroup of G. This thing is G modulo N. This is a normal subgroup of G. It means that when you conjugate it, you stay in it. And this should be true for all G and G. In our case here, everything, conjugation doesn't change anything because the group is commutative. Okay. Now, I want to tell you my questions, what I would ask you. Okay? Well, you're writing still, so I'll wait a bit. I would recommend always asking some questions, not in the lecture necessarily, but if you want, of course. One question here is, what is a good example, a good first example of a group not like this, which is a little bit worse, which is not commutative. These groups here are obviously commutative, which is not commutative. If you're going to say commutative is a property, you should show some nice, you have some groups that are not commutative. And there are many examples, most examples are not commutative, but what I would suggest is the usual idea here is, if you ask me, maybe you couldn't think of a good group to work with, you should send me an email and ask me what is a group to work with, and I would say a group of permutations. Now, as you know, if you have two letters, which is a set S consisting of two letters, 1 and 2, or two numbers, different numbers, then the permutation group here, in my language of analysis 1, as you know, it consists of the identity, and sigma, where sigma is an involution, sigma of 1 equals 2, and sigma of 2 equals 1. So you should always write the stupid example, right? That group, as you know, is commutative. So when you have some idea about looking for a non-commutative group, the first example you look at, you fail. It is not. This is commutative, and it's an important group. The group of order 2 appears everywhere in life. This is the unique group of order 2. So let's try another one. 1, 2, 3. 3 elements, different elements, and you should think about what are the possible permutations of this thing, and maybe this is a pretty big group. We know what its order is, the number of elements in this group. It is 3 factorial. This is a general fact, right? So that's 6. Right? And so we look at what are all possible permutations of that group. And then you ask me, what is a good way to write the thing? One way to write the thing is to write 3, 1, 2 means the permutation 1 goes to 3, 2 goes to 1, and 3 goes to 2. That is the way, that's called the line way of writing. Somebody calls it the line way of writing. You're right, you just write it. Right. Now I believe if you look at this group, which is called S3, because it is the permutation group on 3 letters, and you can imagine what is Sn. There are n letters, and you look at the permutation group. Okay, so this group I claim is an interesting non-commutative group, and so you can check. So that's what you ought to check if what here doesn't commute. I mean, maybe you permute something and then you, so non-commutative means sigma tau, well, not the same sigma, G1, G2 is not equal to G2, G1. That's non-commutative. And so if it's non-commutative, when I was going with this hocus pocus magic here, this thing, the right action, and this thing's a normal subgroup, if the group is non-commutative, what you have learned here by saying, oh, there are non-commutative groups, this is really a condition. Right? Because it says conjugation doesn't do anything at the level of this n. Okay? Let me call this star. Let me call this star. What star means is if you take n and you commute it, this thing is n hat. It does something which depends on g and n, but it's an element of n still. It pushes it around inside of n. Okay. You guys in physics really have to know group theory. Because it is the central point in any kind of physical consideration. So this is an example of permutation groups, these finite groups. Okay. And now the real picture in the case of X will be, as you will see, and I'm going to prove it right now, is that this is the image, so this is the image of X, and the image of X we know is the full C star, and maybe 1 is in the image, here's 1, and 1 comes from 0, and 0, and maybe I will claim it comes from other things, and the picture of X looks something like this. Okay? So you see why I want to have you write it this way. This is C, and here 0 goes to 1, and we're just going to show that there are going to be some other things, but it's a local bihomomorphic map. So locally, it looks like this. You can locally decompose it into little pieces which are locally biomorphic. And as I said before, if you really want, you can call this log 1. And if you really want, you can call this log 2. So there are many inverses. Yeah, the inverse mapping is multi-valued. The way to say it is a multi-valued inverse. This is not new to you because you know the square root is a two-valued inverse. Okay? And the way just to give you a little bit of motivation, you know square root is two-valued. You know square root is defined by a log and so on. So the square root of, I don't care, z looks like this. Here is 0. You see, our colleagues want to take square root of 0. And our problem with the square root of 0 is it's not defined because the way we defined it, the square root of 0, if you would define it, it would be something like x, I don't know, 1/2 log of 0, right? And now that 0 is not in the image of the exponential map, so there's no such thing as log of 0, so that's stupid. So in school, when you were in school, in some place in Albania, for example, I've now got a straight from Albania. When Crystal was in school in Albania, somebody told her square root of 0 is 0, and you should say, no, it's not defined, because square root is defined by something like this. Okay? the point has to be in the image of the exponential map. And you see, if you're outside there, let's take a fun point. Here is the point 1. What's the square root of 1? Plus minus 1, right? So here is plus 1, and here's minus 1. Those are the 2 points that you would get here by inverting here with 2 logarithms. Maybe this would be logarithm 1, and this would be logarithm 2. You will read books and you will find that the authors write something like the principal logarithm. And they have in mind maybe logarithm 1, which takes the square root of 1 to be 1. But quite frankly, I don't care. You just have to say what you're talking about. Okay? So that's the story on square root, and that's the story on the way the exponential map works. And that's what we're going to show now, because this fiber over 1, the fiber over 1, that's the key thing over the number 1 in C star. This fiber is what we're calling the kernel of the mapping, kernel of X. And now we should figure out what that is. Okay? It's worth doing this. The exponential map is obviously a key thing to understand. So, and the group theory tells you to figure out the kernel, and so you figure it out. Right? And then you're finished, because the theory takes over and proves everything. So, what is the kernel of X? And the idea of figuring out the kernel of X, of at least trying to figure out the kernel of X, is an ancient problem. Okay. Figuring out the kernel of X certainly was considered by Archimedes. It is certainly considered, you know the story, it was somehow understood by the ancient Greeks who were in Egypt, because they used the law of sines and all of these various things. So it's an ancient problem, but it is only when you have the exponential map over the complex numbers that you can understand it precisely. So this is in some sense a new thing. Well, I mean, new means 19th century. Okay. So Euler dealt with these problems in a formal way, and in some sense it comes down to the question is, what is an angle? What is an angle? And usually, at least in my high school, we considered a circle of radius 1. Right? And somehow or another, what you do is somehow you draw this picture. Here's the point, here's some point here, and this is somehow an angle. And they draw this picture, and it's not so clear what the picture means. What you can say is maybe an angle is a point on the circle. Right? That is maybe a reasonable thing to discuss. I mean, there are all sorts of things. You discuss these things, and you discuss all that stuff. Right? But the question is, what's an angle? And don't be afraid to ask this question. I'm not going to write it down, but what is an angle, really, historically and in modern times? So what is an angle? So an angle is, let's define it as a point in the circle, which is denoted by S1. The reason the 1 is there, it's one-dimensional, and so that's the one-dimensional sphere. That's the notation S1. So Sn is the n-dimensional sphere. And of course, you're only interested in things that are equivalent to it, for example, by diffeomorphism. N-dimensional sphere in Rn plus 1. In this case, it's in R2. This is a picture in R2, but we think of it as in the complex plane. And the n-dimensional sphere is the set of points x in this Rn plus 1 such that the standard norm of x is 1. So that is the unit sphere. And when you hear somebody talk about the sphere, that's what they mean. Okay? I mean, there are obviously many things that are equivalent to a sphere. So this is the sphere of radius 1 in R2, so this is the unit sphere there. And now look, yeah, if you take, this is by deep thought, you take a point W, let's call this W in the sphere, and the condition that it's in there is that the norm is 1, but you should never write norm, because norm is a bad function. So you should always write norm squared, and that's W times W bar. Right. It's much better than the norm because it has a square root, and then you don't know what the square root means. Right. So that's the norm. Norm is 1. It lies in the thing. And now this thing is x of some point, right, times x bar of some point. In fact, probably many points. We don't know how many, but because there's this kernel that's causing the problem. This kernel that's causing the problem. The kernel in this case this is locally biomorphic, so the kernel in this case is discrete, but in general, this is the general picture. It causes the problem, and you have to understand what the kernel is. And you look carefully at this wonderful function, and you see that x bar is bar of x. X of z bar is x of z bar. Don't tell your mother I wrote that sentence on the board. X of z bar is x of z bar. But it means x bar outside is the same putting bar inside, right? And you know the reason that is the coefficients of x are real numbers in the power series development, right? And you can say x is defined over the reals. That's sort of the slang way of saying this thing. It's good to have a nice slang. It's defined over the real numbers, basically. And now it's a homomorphism. Well, let me start here. It's a homomorphism. This is x of z plus z bar, right? X of z, x z bar. And don't be afraid to write everything down. X of twice the real part of z. Just write it down. And that's a real number. By stupidity, this is a real number because it's a real part of something. And this real number, x of this real number, is 1. X of this real number is 1. But we know the exponential on the real numbers looks like this, right? And if x of the real number is here's the number 1, the only thing that it's actually a real analytic diffeomorphism. The only thing that's mapped to 1 is 0, right? Well, that's sensational because that just says that real part of z is 0. That says that z is in I times the real numbers. That's a short way of writing this thing, I times the real number. Right? So it says that if you draw this picture and you're looking for the kernel is what gets mapped to 1, well, we don't know yet, but if we have this usual picture, you have R, use a complex plane, and we have I times R, and here that's that, and then you ask the question, what is mapped to something in the circle? We have the following answer, x inverse of the circle is equal to I times R. All right, isn't that what we proved? Everything that goes to the circle is I times R. You take any point in the circle, is norm 1. You do this silly computation and you get this. Right? Okay, that's great. So we figured out maybe too much. We figured out something really beautiful, which is about, we're looking for the kernel of this mapping, but what we figured out is X maps IR to the circle S1, and let me even make it obvious, is another group homomorphism. Right? It's another group homomorphism. The preimage of the circle is this thing. The structure here is plus. The multiplication structure here is just multiplication of complex numbers. This is a group homomorphism. You don't add angles in the circle. If you do it in high school mathematics, and this thing is phi 1, and this thing is maybe phi, this is phi 1 here, and this thing is phi 2, and now you're going to challenge me to add those angles. So I have to add this much over here, maybe to phi 1, maybe, I don't know, I get something like this, phi 1 plus phi 2, right? You ask your high school teacher to add 2 angles, and he or she will do that, right? That's not what you're doing. You're calling this number Z1, and you're calling this number Z2, and this number here is Z1 times Z2. Right? The circle is a group. Addition of angles is multiplication on the circle. You've made something precise instead of something blah blah. Okay. So that's what addition of angles is, and this thing is a beautiful homomorphism, and then it's locally a diffeomorphism. Because X was locally biholomorphic, I restrict it to a line, it's locally a diffeomorphism. This thing is not complex anymore. This is just a one-dimensional real manifold. This is another one-dimensional real manifold. And this is very bad because it's a cycle. It's compact. This is wonderful. This is just a vector space. So I replace something here, X, by something which is complicated somehow, a circle, and I replaced it by something we usually call X hat, which is much better. So that's good. We have the circle, and here's the picture of the circle. And now I'm very bad at drawing pictures, as you know, but I go on. It looks like that. Okay? Okay? Because it's the same picture. I've just restricted the exponential map. Okay? And you see, this mapping, which is X, and this is S1, and this is IR, this is locally diffeomorphism, it is surjective, and it's a homomorphism. It's the same thing. I just restricted it. That means I can add angles and so on. Okay? Now, okay. I define a map, which I call E maybe, from R to S1. And now this is really what you learn in high school. That is called as phi, and this goes to X of I phi. Right? That's usually what you do in high school, right? And in fact, quite often you write E to the I phi. Right? That's what you write, right? I know you're bored, but you see, this is very exciting. Writing something down that was considered by Archimedes, considered by Talos, the great Greek who was in Egypt looking at the pyramids. Yes, all of these things are really fundamental. And this thing you write down, and that means here is e to the I phi, some point on the circle, and this has real and this has two real coordinates because this thing is in R2, and this real coordinate is called cosine of phi, and this real coordinate is called sine of phi. That is a definition. And this is also a definition. It's cosine of phi plus I sine of phi. If you're ever, I may be telling you this because later on maybe some of you are teaching high school students, and this is what's going on. Okay. And one of Euler's big jobs, which he did formally but not precisely, and was somehow known to everybody since the beginning of life, but never really proved, was the addition formula. You know what is how to figure out what is the cosine of the sum of two angles, and you want to know how to figure out what is the sine of two angles. And the addition formula is e to the I phi 1 times e to the I phi 2 is equal to e to the I phi 1 plus phi 2. That is the addition formula. All you have to do is put in what is cosine and sine, and you get the addition formula. Okay. So that was somehow known to... So everything that you know about trigonometry is in this picture, having understood it, and the key thing is that you have x, and it's surjective mapping, which is locally diffeomorphism. It couldn't be better. That's everything. Now we're interested in x inverse of 1. So there's a special point 1 here in the circle. We're interested in that because we know that that is the key. That's why it's called kernel. Yes? This is why it's called the kernel of this map. This is the kernel of x, and x inverse of 1 is what is mapped to 1. And well, I don't know, but this is for sure contained in I times R. That much we know, because 1 is contained in the circle, right? And what is interesting is, what is x inverse of minus 1? This is very interesting. This is very interesting. X inverse of minus 1 is something, and x inverse of minus 1 is plus minus some. Already you see, if x inverse of minus 1 is a, then what about minus a? What does it mean? What about x? So x of a equals minus 1. What about x of minus a? Well, this is 1 over minus 1 is also minus 1. Right? Minus 1, I was talking last night to you, which is better, 1 or minus 1? In some sense, minus 1 is better because you know that if you have x inverse of minus 1 is a, then x inverse also of minus 1 is also contains minus a. Right? Okay. And that's wonderful because this implies that x of 2a, which is equal to x of minus 2a, is equal to plus 1. Right? Because 2a is a plus a, and minus 1 squared is plus 1. So we have seen that in the picture here you have IR, and in the picture here you have 0, and you have at least, I call it 2a here, and you have minus 2a here at least. while you have a lot because it's a group. So you have 4A and all this stuff. Right? It's a group. And now, this is what, of course, our classic giants did. They didn't know how to write this down explicitly, but they say, let 2 pi be the smallest positive number in R with x of 2 pi I equal 1. Right? And now, at least some of you who were great students in Analysis 1 last year would say, well, there's some big danger here. We can consider the set of positive numbers with that property, and now you should consider probably something like the greatest upper bound or least upper bound, whatever it is that say. You have to think about, right? It's the danger this thing could converge to 0, right? There's some danger here that this thing converges to 0, and that this doesn't make sense. Right, that it's really not a positive number, 2 pi. It could be 0. Right? This thing, what is it? You go increasing, is that the least upper bound or the greatest lower? Least upper bound. The least upper bound of this set could be 0. Right? It could be. But then you would have a sequence of points converging to 0 in the kernel. A sequence of different points. Right? But the exponential map is a local diffeomorphism. Right? And that means you cannot have a sequence of points going to the same thing. You see, it's a local diffeomorphism, so it says in here, that gets mapped diffeomorphically onto an interval. The only thing in here that goes to 1 is 0, so that the smallest thing makes sense. Okay? Maybe it's at first just a least upper bound, but the same argument goes for every point. If it's just a least upper bound with the sequence business I just mentioned, then that can't be because it's a local diffeomorphism. So this implies then that the kernel of x is 2 pi I z contained as a discrete subset in IR. And it's a discrete subgroup. It's a group, obviously, and it's a discrete subgroup. It can't have a limit point because if you take that limit point, it's a local diffeomorphism at that point. You can't have that accumulation stuff that I just mentioned. Right. Okay? This is wonderful. Well, you know it's a closed set because it's the pre-image of the point, but it's a discrete set, it's a discrete subgroup of the real numbers. Okay. So we know that S1, which is the image of x, is R plus modulo 2 pi I times z. 2 pi times z. I'll put everything in the real numbers and get I out of the picture. Yeah. That's what we really prove. Okay? And what it means is that the picture-wise, you have the circle, and you start at the point 1, and you go around the circle, and you go around and around and around. There's some language that I learned in high school I've forgotten. Radians as opposed to degrees. I think degrees has 360 degrees, and the number of radians is the percentage of 2 pi or something like that. A radian maybe is 1 or is 2 pi, I'm not sure. But okay, so you go around here, and you go around and you go around until you get 2 pi of the radians. And in this space, which this is x, and you start here at 1, the pre-image of 1, which is 0 up here in the real numbers, and you go here somehow. Let's say here's 0. You go, but you're going around here when you're mapping here. This is the exponential map, and eventually you come back. This is the point 2 pi I. And then you go and you go and you go and you go, and eventually you come back. This is the point 4 pi I. That's a complicated picture of what is called a covering space. You should know this word. This is a covering space. This whole picture is called a covering space. This is usually called by me x hat, and this is called x, and this is called a covering space. Oh, it goes on, I have. So, okay. Okay. So we have the kernel of x is 2 pi I. And now, you should ask, how local is local? So the question is, how local is local? In other words, you have a local phenomenon, but maybe you can push it to make it global. And here's the situation. Here is a point in C. So I'm going to call this some point Z0 in the complex plane. This is upstairs in the complex plane, where we have additions. And usually you should use my language, because every mathematician, if you're talking on the telephone to a mathematician and you talk about upstairs, you mean upstairs, and you talk about downstairs. So you have a map going and you say what's going on upstairs, what's going on downstairs. So you should use that language. If I'm talking to somebody, I have x hat is upstairs always, x is always downstairs. So this is upstairs in C. Right? And maybe let's just see let's make now finally a picture of what's going on here in C star. Here's C star. Okay. Here's C star. And now let's see here. Here's 0. So that 0 is not even in it. And here's this point Z0 here. No, that's not the point Z0, that's x from Z0. Okay. Now we have an idea. This is someplace, I don't know where the devil that is, but it's up here in C, so we hear C. And we know that if we fix here, if we fix a line here, nothing happens, because the kernel, the pre-image of this, the kernel moves things from here to here to here to here. The kernel is here, 2 pi, 4 pi, 6 pi, 8 pi, and so on. So here it's Z0 plus 2 pi I, I'll even write it. Z0 plus 2 pi I, Z0 plus 4 pi I, and so on. Yeah, the same thing here. And you have this line along here. This is mapped bijectively, diffeomorphically, onto this line. Right? That's the first thing that you do in high school. It's called polar coordinates. Right? Right? This thing is mapped bijectively onto that line. So that's wonderful. And if I move a little bit, it's a local diffeomorphism. Well, I even am going to do better than move a little bit. I'm going to move in a strip. All right, I'm going to move that in a strip. Yeah, move it up. And I keep this strip a little bit small, and that goes on to something like this. Right? 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 The angle is fixed. This is the angle here, if you like, and this is fixed. And I push, So I'm asking the question, how local is local? So I start with something, I try to push it. So I start with this line where I know it's the diffeomorphism is perfect. I push it, maybe I'm going to push it up, and I push it up, and I get to here, and I say, oh, you could say the nice word in German, Mist. In German, so in English we use other words for this word, which are heavier. But nowadays on the internet I see the English words all over. It's just amazing what words, if I would use these words when I was a child, my mother would beat me. They're so terrible. But of course I use them with my wife. So Mist is a nice thing. This is you have animals in a barnyard, and the farmer, here's the barn, and there are animals in there making their stuff, and the farmer comes out with a tool and makes a big pile, and it's a pile of mist. And there are all sorts of slang. The two Germans, just two Germans here about even small animals make mist or something like that. How does that go? Isn't it something like that?
I think so, yeah.
Kleine Tiere machen auch Mist. Something like that. It's something like, yeah, you see, you guys are some younger generation. I know the old German generation. Okay. Yeah? And now we push this stuff.
Oh yeah, I know, it's auch Kleinvieh machen Mist.
Auch Kleintier machen.
Kleinvieh.
Auch.
Yeah.
Auch Kleintier machen.
Yeah.
Yeah.
So,
Not only the big tier machen big Mist, auch Kleintier machen Mist. So, and you push it here until you get to 2 pi up, and that means you pushed around here, and it's no longer local diffeomorphism because this goes to the same line. Right? So it says that this half-open strip is mapped onto C star. So it says that X of the one half open strip is mapped. Of course, this half open strip is not a manifold. It has boundary. It's a manifold with boundary. This half open strip is not quite, it's not open. It's only open, I mean, you can make many sides that are open and there are all sorts of choices here. But this half open strip is mapped really, at least bijectively, onto C star. Okay. Okay. And now you can pay your money. Life is capitalistic. You can take the blue half open strip or the green half open strip. There are all sorts of things you can take. Even if you started here, you could start at, let me even just mention what you could have done, and many people do that. And now I need a color. Many people do that. I don't do much of this. You only go halfway up here, and then you go halfway down. Right? The only thing is that this thing, if you translate it by 2 pi I, you go out. That's the key thing, because that's what you're doing here. So there are all sorts of things. These things quite often are called logarithms. The inverse map is a logarithm. It is well defined and is determined by a half open strip. Okay. So now, if you are teaching elementary mathematics, even to college students, but in particular to high school students ever, you now know precisely what is exponential math, logarithm, trigonometric functions. You know all. Okay. Now, I spent way too much time on this, but I think maybe it's with what? And furthermore, I like it. So application. Applications of the normal form. Okay. let D, here's the first application. Let D be open, connected, in the complex plane. And F a holomorphic function. Assume that F is not identically a constant. Then F mapping the domain to the complex numbers is an open mapping. What does it mean, open mapping? So, recall, I know mistakes that you guys are terrific, you never make mistakes probably, but I know all mistakes that beginning mathematicians, including myself, made. What does it mean a map is continuous? It means the inverse image of open sets is open. Right? That's what continuous means. So that means the inverse image of open sets is open. An open mapping means the image of open sets is open. It's two different things. One is the inverse image, that's just continuity, and the other condition is the image of open sets is open. So let me put that right here. Images of open sets. Image of open sets is of an open set. I don't know what, of an open set, of every open set, of every open set, open subset of D is open. You have little experience in mathematics, let me tell you that's a hammer. To know that a mapping is open is really big time. The image of every open set is open. That is a big time. So you should keep in your mind three things. Pre-image of open is open. That is the condition of continuity. You know that. Pre-image of open set is open. Image of open set is open. Is open. This is a big condition. And we say in this case that the mapping is an open mapping. There are four things that you should keep in your mind. These are two of them with open sets. The other thing, two things you keep in mind are with compact sets. Image of a compact set of compact sets is compact. This is implied by continuity. So maybe I call this 1, and I call this 2, and I call this 3. And from my point of view, because everything in this course is more or less continuous, or I can reduce to continuous. 1 and 3 are trivial. Okay. 2 is not trivial. The image of any open set is open. And 4 is exactly the other point. Pre-image of compact is compact. And this is a big condition. And this condition we call proper method. This is a fundamental condition, and it's fundamental to try to isolate when you have a proper method. Pre-image of compact is compact. Okay. Pre-image of compact is compact. To tell you how new all of this is, these first 3 conditions probably were apparent in mathematics even rather early. This 4th condition was introduced by Henri Cartan in 1930s because he realized the importance of this condition, properness of a mapping. So we will talk about it later on, but I just wanted to mention 4 topological type of properties of mappings. Pre-image of open set is open, image of open set is open, pre-image of compact is compact, image of compact is compact. Okay. Well, I haven't proved it yet. If it's not, here's the proof. Now, I'm emphasizing with drama that this is a trivial consequence of the normal form. I'm putting this in a little box here. Yeah? Locally, F is equal to whatever it is, a constant, plus W to some number N. Remember, somebody asked in their homework, I'm not sure who it was, whether we assumed f of 0 is 0 for the normal form theorem. It's really up to translate. We translated, or I think Jasper asked it. It's just a notational simplification. So we have its value at the point, whatever it is, plus normal form theorem. Okay, locally. Well, the map W goes to W to the N is an open map. This is trivial. You can check it with polar coordinates or whatever you want, okay? That is the proof that it's locally that, and that's true for every such thing because this domain is connected. Remember, the assumption here is that it's not identically 0. That means it's never locally identically 0. So you're really using here probably the identity theorem. Yeah. That's the proof. Well, let me just comment that Gauss was what we call differential geometry in some sense. And he knew somehow this theorem should be true because he knew somehow that holomorphic mappings are conformal. But he could not formulate this theorem. This theorem was first formulated, I've even seen the paper, by Schwarz. So there are many Schwarzes in mathematics. There are, for me, 2 Schwarzes that I use every day of my life. And this Schwarz is this guy, H.A. Schwarz. I know many stories about him. He was, of course, German and very interesting, proving very many interesting theories. He formulated the notion of open map. Now, let me tell you some history, because you need to know how you fit into the history of mathematics. Yeah. There was a great Polish school of what we call general topology. General topology means what we call point set topology. This was in the 20th century, maybe in the first 1/3 of the 20th century were the first results. But you must understand that the first decent textbook in general topology that was available in the United States was written by a professor in Berkeley named Kelly, and he wrote it after World War II. So that emphasizes the newness of this point set topology. I'm talking about notions like open, close, what is a topology, what means compact, right? And when I was a student, I didn't do it because I hated it, but there were courses in general topology. It's very, as you can imagine, it's very close to logic, right? It's very close to logic. And I hated it, I didn't do it, but I picked it up by teaching myself. And that's what you all have to do nowadays. This is going out of style. There's no such thing as a course in general topology, right? So you have to pick it up yourself. One thing you have to pick up is the things I'm using here, okay? So this is, I just put here, it's a rather new subject, but you have to pick it up yourself. Now, one person who made absolutely fundamental contributions to this, and I'm greatly proud that I've lived very near where he was, and I walked down the street named after him, which has the streetcar named on the street, yeah, is Hausdorff. This was an incredible intellectual who understood really what is going on in general topology. He wrote down the first axioms and so on, so, called separation axioms, written down by Hausdorff. And when I walk down Hausdorff Street in Bonn, I think about Hausdorff, and I think about really nice things that are not Hausdorff. Now let's recall, what is Hausdorff? Hausdorff means you have a topological space X, you have 2 points A. I think this is what it means. I always have to ask myself, in this, which you have 2 points which are not, one's not equal to the other. And you put a little point here, here's X1, here's X2. And then the statement is, I think this is Hausdorff. Does anybody here remember? There exists open sets U1, UI, open neighborhood of Xi, such that U1 intersect U2 is the empty set. Is that Hausdorff? Huh? Okay. You can separate points by open sets. It's a fundamental thing. It's absolutely fundamental. In complex analysis, all of the sets that I deal with are Hausdorff, all of the topological spaces. Yeah? But we learned actually very early in the game from algebraists, for example, Zariski and Samuel, who wrote the first decent commutative algebra book in the background of algebraic geometry. We learned in the early part of the game that the correct topologies for algebraic geometry are never Hausdorff. So just because something is Hausdorff, we like it, it's Euclidean, it's everything's cool, you're walking around smoking cigar, drinking cognac, right? Hausdorff spaces are not necessarily ubiquitous. And now let's think about my picture. my picture of upstairs, and my picture of downstairs. So, you know I'm very optimistic. You should be optimistic, and then you should check yourself. So my picture is upstairs and downstairs, and a mapping. And you have the fibers of this mapping, all these fibers of this mapping. Here are the fibers of the mapping. This goes down to a point here, X. This is X, maybe, and this is maybe X hat. And we upstairs, we have these things. And now, we want to know what is a good open neighborhood of X. Yeah? So upstairs, let's say, is a topological space. And you want to know what is a good neighborhood of X downstairs. Well, you all know that this is an equivalence class. These things are the equivalence classes. And this whole equivalence class is really X. This is a partition of the space, so X, this is an equivalence class. This is the point X. So a neighborhood of X is a neighborhood of the equivalence class. So let's draw it in color so you understand it. You define, if you have a mapping here, pi, I don't care what it is, you have a neighborhood of pi is by definition an open neighborhood here. So, okay. And now the question is this downstairs topology Hausdorff? Okay? That is the question. So are you ready? You're thinking, watch. Okay. Let's take the circle. One. Let's take an angle phi, which is an irrational angle. Do you understand what I mean by irrational angle? Irrational multiple of 2 pi. Do you understand? If you have a rational multiple of 2 pi, if you add it up and add it up and add it up, you're eventually going to get back to 1. Because it's n times m. N divided by m times 2 pi. But let's suppose it's an irrational angle of 2 pi, and you know what happens, I hope. You learned about this when you were in school, right? The group generated by this thing is dense, right? The group generated by an irrational angle is dense, a dense subgroup of the circle, right? Okay. And now you can imagine. Here's my picture. Here's upstairs. Here's downstairs. Here's the fiber. Well, that's the fiber over. I don't know. This is this group. It's dense. This is a fiber here. It's dense. This is a fiber here. It's dense. This picture, I hope you understand, is a big lie, right? Because it said, what is true is, I take a point down here, the equivalence class is this, I wanted to find a neighborhood to be here around this, and it's just like this. But in fact, every other orbit of this this dense group comes in there. You can never separate things down there. Do you understand what I'm saying? You can never separate the two things by open sets. So, in other words, if you take the orbit of some point here and go around and take the orbit of another point here and go around, there's no way to separate them by open sets. And now Nico was talking about the other day about torus. Right? Well, let's do the same thing. If you take a torus, I'm sure you had in mind from high school, a torus is a rectangle with sides identified. Right? Right? And now you have a line in here, which is perfectly good. But let's say a line in here is a line like this, is a line like this, and so on. A line on here, depending on the angle you're talking about here, is either closed or dense. right? The line in there is either closed or dense, right? So if you take two different lines, you think they're different, one starts here and one starts there, you will never separate them because they come back around each other and you cannot find neighborhoods which are disjoint. So in the quotient topology, this is called, you have to think, what is the quotient topology? In the quotient topology, when you're talking about lines going around in the torus, yes, any parallel lines, they always come back onto each other because they're dense. If you take the groups here generated by irrational angles and you look at an orbit of one of the groups here and then you take another orbit and so on, they all come, you can never separate those orbits. So this picture is a lie. Yes? This picture of separating these things and having the quotient topology is a lie. So, right? Right. The quotient topology is not Hausdorff. Okay? And this is mammoth, as soon as you take quotients, it's a mammoth condition that the quotient topology is Hausdorff.
Could you repeat this line, please?
Yeah.
Specifically about the circle and
You have fibers of a map. And now I have to stop because you want to go to lunch, but let me repeat it. You have fibers of a map, all these fibers. What you would like is that defines an equivalence relation. Now, upstairs is a topological space. And who knows what this map is? I don't know. Yeah. Now, downstairs you would like to get a topological space. You regard this thing as an equivalence relation. So a point downstairs is just an equivalence class. Right? It's just an equivalence class. So you say, well, a neighborhood of this equivalence class is a neighborhood of upstairs equivalence class. So that's what it should be. Okay, fine. And now what you would like is that you can separate points downstairs. Right? And now if if this equivalence class has this equivalence class in its closure, you will never have a neighborhood of this equivalence class which is disjoint from this equivalence class. Because this one's going to come over there close to it in its closure. Okay? So it's a very dangerous thing, and that's all I'm saying here. I gave you two examples. One with irrational rotation, but it's the same example actually. Maybe it's more familiar with the torus. Right? You take a line, which is a perfectly good, say through the identity, which is a perfectly good subgroup, and you just push everything along with this line. So that means parallel things. But in the torus, they come back onto each other. You see that, don't you? Because of the irrationality of the angle, these lines come back onto each other. Okay? So I just want to say that Hausdorff is a condition that I always have in my head, but it's very hard to achieve in some situations. One is the situation of quotients. Two is the situation of algebraic geometry. And so just keep that in your mind. Okay. Now, you need to go to lunch, probably? Is it okay to meet back here around 1 o'clock? Yes?
As I understood, isn't that the set of all irrational angles is considered as a one equivalence class, right?
No. I didn't maybe explain this well enough. No. I take one irrational angle, okay? And now I rotate, given a point, I rotate it by that irrational angle and all possible multiples of that irrational angle.
Yeah, and it goes all over the...
It's dense. It's dense. Yeah. Then I take another point and rotate that as well.
Another irrational angle?
No, another point in the circle.
Any point?
Any point. I fix the irrational angle. It generates a group, 2 rotations, 3 rotations, and so on. I take a point, I make all these rotations, it's dense. I take another point, I make all those rotations, it's dense. These two dense sets are disjoint. If, well, almost always, if I take, right? I could, okay.
but this dense set has this dense set in its closure. So there's no way to separate those two things. So Hausdorff is a crazy notion for dynamical phenomena. As soon as you have any kind of dynamical phenomena in this situation where, of irrationality, for example, you're going to meet this. So let's meet back here if we can around 1 o'clock. Okay.